Welcome to Part 2 of Scanning Thermal Microscopy Basics. In this part of the presentation, you will learn about the different types of scanning thermal probes and readout circuitry. This presentation has been brought to you by PicoCal and has been written by Amar Basu and Angelo Gaitas. There are two types of thermal probes. They are classified by the way the temperature of the probe is monitored. The first type of probe is a thermocouple probe. In this case, the probe temperature is monitored by a thermocouple junction microfabricated at the probe tip. You can see in the diagram here that we have two dissimilar metals that are joined at the apex of the probe tip. In this type of probe, the voltage that forms across the two metals is proportional to the tip temperature. In a microbolometer probe, the probe temperature is monitored by a thin film resistor at the probe tip. So this acts very similar to an RTD type sensor. In this case, the resistance is proportional to the tip temperature, and the resistance is monitored during the course of the scan. One of the advantages of thermocouple-based probes is that they offer a direct measurement of the temperature. The metals are chosen based on the Seebeck coefficient. Common combinations include chromel-alumel, gold-palladium, gold-platinum, and gold-nickel. The typical Seebeck coefficients for these metals is on the order of 1 to 20 microvolts per Kelvin. Polysilicon is also used, and this offers a Seebeck coefficient 1 order of magnitude greater. The fundamental detection limit of thermocouple-based probes due to electrical Johnson noise under typical conditions is less than 10 millikelvins and is given by the following formula. Delta T noise is equal to the square root of 4 kTr delta F over S. S in this case is the sensitivity of the thermocouple probe and is given in volts per Kelvin. K is the Boltzmann constant, T is the temperature in Kelvin, R is the electrical resistance of the probe, and delta F is a measurement bandwidth. We'll see later that one way to reduce the noise is by reducing the delta F by using lock-in-based techniques. Microbolometer probes have a resistor near the tip which can be used to heat the probe and simultaneously measure its temperature. The bolometer probes offers a simpler structure and device fabrication than thermocouple probes because a bimetallic process is not required. The resistor metal in this case is chosen based on the temperature coefficient of resistance, or TCR. The electrical noise which was derived for thermocouple probes also applies to bolometer probes as well, except that the sensitivity in this case is the change in resistance over the change in temperature. One of the advantages of microbolometer probes is that they offer two modes of operation. In the passive mode, the resistor is biased at very, very low power. This type of mode is useful for measuring the sample temperature. Essentially, it acts just as a thermometer. In the active mode, the resistor is biased at high currents so that the probe tip is heated higher than the sample. In this case, it can be used to measure the sample heat conductance and the heat capacity. So these two modes of operation can both be used with the same probe that is manufactured. Let's take a closer look at the structure and the operation of active bolometer probes. These are the types of probes which are used more often in research settings today. If we look at from the top view, the probe consists of two light blue metal lines which represent the electrical leads going into the tip of the cantilever. The dark blue horizontal line near the top of the cantilever represents the Joule heating element, which is much thinner than the electrical leads leading out into the tip area. From a three-dimensional point of view, we can see in this movie that the tip is right under the bottom of where the heater is. When the heater is activated, the tip heats up, and then the probe is lowered to the surface to do a scan. As the probe is scanned across the surface, the tip temperature changes depending on what type of material the probe is being scanned over. In this case, as we saw here, the probe was scanned over gold lines, which has a high thermal conductivity, much higher than the green PCB substrate, which is represented by the green regions. So if we monitor the tip temperature over the course of the scan, we can get a thermal map or thermal image of the sample. In order to measure the temperature of the probe, we have to have an appropriate readout circuit. This circuit is typically a Wheatstone bridge, which is a very straightforward circuit, and this circuit provides a fixed power and simultaneously measures the resistance of the probe. The Wheatstone bridge consists of 4 resistors, one of which is the probe resistance. On the opposite leg of the bridge, where the probe is, there is a control resistance. At the beginning of the scan, this control resistance is adjusted to match the probe resistance. During the course of the scan, as the probe resistance changes, the output from the Wheatstone bridge will generate a signal at the input of the amplifier. The amplifier will amplify this with the gain of A, and then we have an output signal represented by V0. The sensitivity of the circuit is given by the following equations. S is equal to delta V over delta R. Delta R is the change in the probe resistance, and this is proportional to the gain of the amplifier. It is proportional to the supply voltage Vs, which is supplied to the bridge, and it is inversely proportional to Rp plus R1 squared. This is a very straightforward circuit which can be used to monitor the temperature during the course of the scan. The previous circuit, as we saw, was biased the probe at a constant power. But as we can see that there's actually a different type of mode, which is called the constant temperature mode. This mode is very useful because we can make sure that the tip temperature stays fixed rather than changing during the course of the scan. And the way the system works is that a servo control adjusts the power running through the probe in order to maintain a constant temperature. The advantage of a constant temperature mode includes improved linearity, speed, and reduced damage to samples. Just 2 examples that are shown here. One again where we have the low thermal conductivity or the high temperature material. In this case there's low heat flow to the tip, and in this case there is low power required to heat the tip. Contrast that with the case where there is a high thermal conductivity or low temperature material, in which case there is a high heat flow between the tip and the sample. In order to maintain the same probe temperature as with case 1, we have to increase the power to the tip. But notice that in both cases the temperature of the tip remains the same. The servo control circuitry used to bias the probe in the constant temperature mode is very similar to the simple Wheatstone bridge circuit that we saw earlier. The only difference is that instead of having a fixed voltage supply Vs, the output of the amplifier V0 is fed back into the top of the bridge. The circuit essentially adjusts power to the probe in order to maintain a constant resistance, in order to maintain Rp is equal to the control resistance Rc. If the bridge supply voltage, in this case V0, is increased, there will be more power supplied to the probe, in which case the probe temperature and Rp will both go up. So you can see that the feedback mechanism works by stabilizing the resistance so that Rp is equal to Rc, and this maintains a fixed temperature in the probe. In this type of circuit, the probe temperature can be user-defined by adjusting the control resistance Rc. A higher value of Rc will result in a higher biasing of the probe temperature, and vice versa. This concludes part 2 of the presentation. Please continue to part 3 to learn about lock-in techniques, different variations of scanning thermal microscopy, and a brief history.